These students studying further mathematics are taking part in an activity to help deepen their understanding of complex numbers. The activity involves categorizing complex numbers according to their properties. The properties labelled here, A, B and C, are set out in a Venn diagram. Their task is to find pairs of complex numbers that satisfy each region. The students are given no further instruction other than what is written on the sheet. In this video, we observe students as they tackle the task and also hear the reflections captured after the lesson describing how they approached it.
If W is the complex conjugate.
Because the only way that way would work is if W was exactly the same as Z. To get this bit here, which we can't do because otherwise it would have just not, it wouldn't be a question, would it?
No, there's not that.
So that's not.
And then simplify.
We need another way to do this.
A plus BI.
Is it this one?
And we're going to call this one C plus DI. We're saying A times C must equal BD.
BD, yeah.
Then they cancel out.
We could just fill in the other parts for now.
That's the other part.
Like something that satisfies that and that, something that satisfies that and that, something that satisfies that. Not all three at the moment, and then we can work it
Yeah,
out
because that would
from
be the
there.
hardest bit.
We started off with, on the Venn diagram, working out the other parts rather than the middle part first, to kind of get an understanding of the actual ideas.
We're saying this has to be like the negative of that, or that has to be the negative of that. Because if we want it to be imaginary
Yeah,
only,
there's got to be no.
those two have got to be the same as that one.
Yeah.
But it's got to be
Yeah, it's got to be the
imaginary
negative.
part.
for-
Yeah, so one of those has to be negative.
We kind of tried to work out general formulas and a couple of examples for B and C, and then we found a link between A and B, and a link between A and C, but we didn't actually get any further than that, and that's when we moved on to the technologies to see if we could actually find exact examples for the links that we'd found.
Yeah, we kind of did the same, starting off with written work and then going on to the technology to understand it further when we got a bit stuck. Is there any other place where Z times W is real?
I don't think it's going to work for what we set Z as.
We started using the app with trial and error. So we first started off with Z as 1 plus I, and we moved W around the circle because that is where the modulus is the same. And we was looking for points on that circle where the ZW is real, so ZW had to be on that line, and then the other one had to be on that line. And we realised that for when Z equals 1 plus I, it doesn't work. So then we thought about it with other points like 2 plus I and 1 plus 2I, and then we thought what would happen if it was just imaginary. And then from there we realised that W and part B were the same, so then we thought if we moved that to the imaginary axes, that would be real. And then we found a pattern between the middle part where it could be Z equals XI, and then as long as W equaled minus XI, then it would always go with each property.
Can you find anywhere if Z times W is real,
2.5.
but they're not complex conjugates?
Z times W is real.
Yeah.
We kind of did the same thing, except we were using it to prove the connection between A and C. We made the modulus the same, I think, and then we found points where they were the same, and then we found points then where ZW was on the real axis, so therefore was a real number, and we found that they effectively had to be with the imaginary components being conjugates of each other.
Yeah.
There.
Those nice little numbers.
Well, you've got
2
1
minus
and
2.
2. You've got 2 plus I Z. Is it possible that it's something to do with the fact that they're half of each other? Having looked at that.
1 plus.
Because that,
If you
that's
times that by
half
1.5 and times that by 1.5, you get that. So the scalar multiples.
No, I think the fact that where you're doing everything together means that you're practicing all of the skills in in sequence rather than just doing one at a time like you would in a textbook exercise. Because if you just do 10 questions on adding complex numbers, you're then not using the multiplying or finding the moduli. So it's a way of combining all of the skills together, which I think is good.
The question is also a lot more longer and more detailed and quite more difficult. So working as a pair for a question like this, it was a lot easier to understand the topic, and you could kind of understand what each property was meaning because you could share your understanding with the other people.
You kind of learnt patterns of, so two conjugate imaginary numbers would multiply to make a real number, and it kind of enforced that fact, so it developed that knowledge more with the differences in negatives and positives and what they do with the different numbers.
Plus 2 plus I. I'm going to put, we'll call it A.
What's that?
Z star. 4 plus 2I. So what we're saying is that works for A only.
Could you do it
Minus 1.
just thinking in the diagonal?
You can't answer that bad.
So if you did it minus 4
You can't answer that bad. Oh god.
Minus 2.
does that work?
Yes, it does. So
4 minus 4 minus 2I, which then equals minus 2.
So
That works for
goes
A and
there.
B.
Do you want to write it in?
Before, when we first did it, I found like modulus and argument quite difficult because we was learning something new that we hadn't learned before, and coming back to it and thinking about it more detailed and complicated with another person, it helped understand the idea of complex numbers altogether a lot more.
I found that, so I struggled with the idea of conjugates and how they all related, and I found that this activity specifically worked really well to like help that and develop that understanding more.